Hi, my name is Yuwen Xiong. Today I'm going to introduce UPSNet, a unified panoptic segmentation network. So given a 2D image, the task of semantic segmentation produces pixel labeling without reasoning about instances. Instance segmentation approaches detect and segment every instance separately, but cannot deal with uncountable regions such as sky, road, or grass. In most application domains, we not only want to get things, but also infer the environment, that is, the stuff. In this work, we focus on panoptic segmentation, which combines these instance and semantic segmentation tasks. So previous work in panoptic segmentation suffers from redundant computations, as we need to run a model for each task. These results are then combined with heuristics to get the final panoptic predictions. As a consequence, existing approaches cannot exploit joint inference well and result in architectures that are not end-to-end trainable. In this example, the semantic segmentation model should easily segment pedestrians. However, due to the heuristic merging rule, it will only trust the instance segmentation model, and therefore results in poor segmentation at the boundaries, leaving unknown black regions. In contrast, for our end-to-end trainable panoptic network, even though the matrix of instance and semantic segmentations are almost the same compared to the baseline, the final output is a learned merging logic that results in much finer boundaries. Let's now go over our model. So we employ a single backbone with FPN to compute features for both tasks, thus greatly saving computations. The features are then fed into two task-specific heads, one for each task. The first one is our newly proposed semantic head to perform semantic segmentation task. As the instance head, we simply follow Mascasian. The output of the two heads are then fed into a panoptic head that produces panoptic logits. We perform pixel-wise classification over these panoptic logits, just like semantic segmentation, to get a consistent estimation. We solve the conflicts between the two tasks in a principal way by exploiting a learnable model. Thus, no heuristics are required. Note that our semantic segmentation head is a novel architecture with deformable convolutions. In the interest of time, we're skipping the details here. Please check the paper or come to our poster session for in-depth explanations. Next, I'll explain the details of the panoptic head. It takes the output of semantic and instance segmentation as input. So we first resize and pass the mask logits from the instance heads to the same resolution as the raw image. And we split the semantic logits into two parts, thing and stuff. We crop patches from the relevant class channel and add them to the padded mask logits to form the thing logits in the panoptic output. And for stuff, we simply append the logits to the panoptic ones to serve as stuff predictions. To resolve the conflicts between the semantic and the instance head, we construct a one-channel score map which contains logits for pixels where instance head doesn't make predictions while semantic heads predict instance here. We call it an unknown channel that helps us to handle the conflicting part. If this channel wins after a softmax for a pixel, we leave unknown there. This forms the final panoptic logits. We now show our quantitative analysis on COCO and Cityscapes dataset. The baseline uses separate Mascasian and PSPNet models and heuristics to combine both outputs into the final predictions. Even though our model's capacity is much lower due to a single backbone, it achieves better performance with less runtime. Here is a visualization of our models on Cityscapes. The results show segmentation done independently per frame without any temporal smoothing. As we can see, the level of detail captured in the instance is high. The number of black regions is very small, which means that the join task does its job very well to explain all pixels rather than having larger unknown regions like the heuristic merging logic. Thanks for listening and see you at poster 55.
Good morning, everyone. My name is Hugh from Singapore University of Technology and Design. And today I want to talk about John's semantic-instance segmentation of 3D point clouds. So given an input of 3D scene, John's semantic-instance segmentation is a problem where we have to solve both semantic segmentation, which predicts per point semantic labels, and instance segmentation, which associates every point to an object ID. Here we show that the joint task will outperform each individual components. So in recent years, we have seen a lot of methods for 3D deep learning on point clouds. This work often focuses on network design, classification, and semantic segmentation. For fully scene understanding, here we have to consider a more challenging problem, joint semantic instance segmentation. So here we propose a method to perform joint semantic instance segmentation on 3D point clouds. Given a 3D point cloud, we first scan the entire point cloud by overlapping 3D windows. Each window is passed to a neural network to predict the semantic labels and the instant embeddings. This embedding can later be used to cluster points into different instances. Our main contribution are a multitask bond-wide network, MTBNet, and a multi-value conditional random field model to jointly optimize the semantic and instant prediction from our networks. Our network is based on the feed-forward architecture of PointNet. The network is diverged into two different branches, performing two tasks: predicting the semantic label for 3D points and creating their instant embeddings. The loss of our network is the sum of these two branches, the semantic prediction loss and the instant embedding loss. For the semantic prediction loss, we use a usual cross-entropy loss. The instant embedding loss is defined using the mean discriminative loss function. So here we explain the embedding loss in more details. It consists of three different smaller loss functions: the bool loss, the bush loss, and the regularization loss. The bool loss, calculated by the hint loss between the embeddings and their centroids, attract the embeddings toward the instant centroids. The bush loss, on the other hand, keep these centroids away from each other. The regularization loss acts as a small fork to draw on the centroid towards the origin. For the CIF model, we consider each 3D point as a node in the graph. Since each node can be associated by two labels, semantic and instant, we call our model multi-value conditional random field. We jointly optimize these two labels together. The first two terms of our CIF performing semantic segmentation through a dense conditional random field model based on the prediction of our networks and similarity between neighborhood vertices. Similarly, the next two terms perform instant segmentation based on the embeddings and 3D geometric and appearance information. The final term encourages the consistency between semantic and instant labels. For example, if two nodes are assigned into the same instant, they should be assigned to the same semantic label. To represent this cost, we use the entropy of the semantic labels inside an instant. We evaluate our method on two datasets, the S3DIS and CNN dataset. For semantic segmentation, we evaluate the performance using accuracy. For instant segmentation, we calculate the mean average precision asymmetric. Here are some qualitative results of our method on S3DIS and CNN. We also compare our method with other state-of-the-art networks, such as PointNet, PointWide CNN, or SGPN. Our method achieves state-of-the-art performance on the semantic segmentation task and show competitive results in the instant segmentation task. Thank you for your attention. Please visit our poster for more details.
Hi, good morning. My name is Davy and I'm presenting our work on real-time proposal-free instance segmentation with the title Instance Segmentation by Jointly Optimizing Spatial Embeddings and Clustering Bandwidth. This is a joint work with Bert, Marc and Luc and is done in collaboration with Toyota Europe. So, what exactly is instance segmentation? Well, I think that by now everyone is aware of the standard semantic segmentation in which we want to determine the semantic class for each pixel and which is displayed in the middle image for class segmentation. Now, instance segmentation differs in the fact that we not only want to indicate the semantic class, but we also want to be able to distinguish between the unique objects in the image. In a sense, we can say that instance segmentation is a more elegant way for object detection than the standard bounding box approach. Now, an effective proposal-free method for instance segmentation is to assign pixels to a specific object by regressing offset factors to point at the object center. For this, previous works use a standard L2 or L1 regression loss function for learning these offset factors directly. However, although learning these position relative offset factors is promising given the spatial invariant nature of convolutional networks, there are, however, some downsides to this straightforward method. A first downside is that the regression loss, although correlated, does not directly optimize for mask IOU, and this because the pixel clustering, which is done in the post-processing step, is not included in the loss function. Therefore, this loss is not end-to-end optimizing for mask segmentation. A second downside is that this loss function is very strict for distant pixels, forcing them to point directly at the object center, which is both difficult and not necessary, and in a way negatively dominates the loss. Now, to solve these issues, we've developed a new method inspired on embedding loss functions. Our method integrates a soft differentiable clustering within the loss function, and by doing so, it can optimize the mask IOU end-to-end. First, we shift all pixel coordinates with the predicted offset factors, forming what we call spatial embeddings. See figure in the bottom left. Next, during training, we iterate over each object and apply a soft clustering onto these spatial embeddings. We do this by applying a Gaussian kernel centered at the specific object centroid onto the embeddings. This function converts the distance between the spatial embeddings and the object center into a probability of belonging to that specific object. The probability map can be seen at the bottom right. The smaller the distance between the embedding and the object center, the higher the probability will be. Therefore, this probability map resembles the background-foreground map of each object. This way, we can now optimize this probability map directly with the Lovász-Hinch loss function, which, instead of the standard cross-entropy loss, is a segmentation loss function for optimizing the intersection over union. Note that in contrast with previous methods, we do not directly apply a loss onto the offset factors, but backpropagate through the Lovász-Hinch loss, which in turn forces the spatial embeddings to lay closer to their respective object center, maximizing the intersection over union. Now, instead of using a fixed sigma, which represents the clustering bandwidth, we make sigma a learnable parameter so that the network can learn an optimal clustering bandwidth for each specific object. In this way, for large objects, as you can see, the bandwidth can increase, relaxing the loss for distant pixels, as can be seen in the image below. Now, our final pipeline looks as follows. With the explained loss function, we train a branched network for instance segmentation. The bottom branch predicts the offset factors and the object-specific sigma values, which we have discussed in the previous slides. Combined with a class-specific seed map to identify the object centers trained in the top branch, we can retrieve the different instances in the scene. For more details about the seed map, you can pause by our poster or find more details in the paper. Now, since our focus was on the development of a real-time proposal-free instance segmentation method for autonomous driving, we evaluated our method on the challenging cityscapes benchmark. By running at more than 10 frames per second on 2 megapixel images, we show that our method is fast, making it ideal for real-time applications like autonomous driving or industrial applications. Not only is our method fast, but we also show that our method results in good accuracy, with even a 5% improvement over the popular Maskar CNN. This way, we present the first proposal-free method which is able to be competitive with the popular proposal-based ones. So, thank you for your attention, and for more details, you can pass by our poster or read our paper. Thank you.
Are there any questions? Okay, if there are no questions, feel free to just stand up and stretch. You have a question.
So I have a question for the first paper. You pitch yourself against the approach where the semantic segmentation and instance segmentation are merged heuristically.
Yeah.
So I wonder, in your approach where you learn them separated and learn how to merge them together, which classes gain the most benefit? Can you offer some insights? Where the biggest gain is, or where the biggest loss is?
You mean the big scan about learning
the way to combine the results in a parametric way.
Yeah, so our finding is that by learning to merge them, we can improve the instance segmentation by using the semantic segmentation information, because sometimes semantic segmentation can do very well on the boundary. Yeah. And we didn't do any failure case analysis, so we cannot tell you what was the most lost part. Yeah.
For the second paper, you had your results against the mask RCM, for example, on the doors and sofa classes, your performance is much worse. I wonder if you have any explanation for those.
The result from the instance segmentation for these guys are worse because I think it's because of the imbalance in the training data, where the door and on like these small objects has less training data than the like other classes. So the semantic prediction performance is lower than usual. So it's also affect the instance segmentation prediction because the instance segmentation class depends on the semantic predictions.
Oh, there are questions.
Yeah, hi, there's a question for Davy. This Gaussian probability assumption, does it have any effect on the shape of the objects? I've seen pedestrians, but could you segment donuts?
Well, you can in fact segment donuts actually very well because the offset factors are still regressing to the center of the object, right? So this is what the this Gaussian density or this Gaussian function does. It just does a soft clustering, but the offset factors are still pointing to the center of the object. So indeed, for donuts, it would be very well.
Okay, we have to, okay.
And the background pixels, they move. They don't point at the center. So.
Okay, thanks everybody. We're missing a speaker for the next session.
Yeah.
Go, yeah, please come up. Yes.
Hi, good morning, everyone. The title of my presentation is Deeper CO3, Deeper Instance Co-segmentation by Co-segmentation and Co-saliency. My name is Quang-Jui, and this is a joint work with two engineering advisors, Yuwen and Zhao. In the past years, significant progress has been made on object detection, semantic segmentation, and instance segmentation. However, most existing methods require sufficient training and attention with the predefined classes, so they can work only on unseen object classes. So, to overcome this issue, given an image set containing the common objects, many works for object localization and co-segmentation has been proposed to localize and segment the common objects. In this work, we address a new task, instant object co-segmentation. Given an image set, we aim to detect and segment all of the instances belonging to the common category. Okay. Our contributions are summarized here. First, we propose a new task called instance co-segmentation. Second, our method runs in online fashion and there's no training stage. Finally, we collect 4 data sets for this task, and our method achieves the state-of-the-art performance. Our method is inspired by the observation peak. A peak often corresponds to the strong visual cues residing inside an instance. In this work, co-peak is proposed, and it means a pair of peaks, one for each image on the 4D feature cohesion tensor. For example, given 2 images, we extract the feature map and perform the correlation to produce this tensor. Then we call a picker in this tensor a co-picker because its corresponding pickers are inside the arbitrary instance and similar to each other. Finally, we can trace back to detect the instance. Our approach includes two stages, co-picker search and instance mask generation. In the first stage, 3 losses are optimized. First, we introduce the co-picker loss. In this loss, we jointly detect and stimulate the co-pickers. Our method detects the co-pickers with a local window and then stimulates the co-pickers with a local loss. Then the affinity loss is given. This loss helps learn more discrete features that can separate the instance from the background. Specifically, this loss encourages the high feature similarity between the two pixels that are both salient. Otherwise, reduce the similarity. Finally, the static guided loss is shown. The goal of this loss is to identify the salient region. Given a predicted map, we first change the sense prior and then minimize their difference. Finally, given an image set, we optimize the 3 losses to detect the reliable co-pickers. In the second stage, we follow the previous work by Zhao et al. The top-ranked object proposal for each detect co-picker is retrieved by referring to our co-sense map, our background map, and the instance response map from the previous work. We introduced the 4 datasets for evaluation. The first one is VOC12, and then we separate the COCO dataset in COCO VOC and COCO non-VOC. COCO VOC contains the classes that are also covered by VOC12. The final one is SOC. We use 2 types of the existing method as our baselines, including object localization and instance segmentation. Our method achieved the best performance on the 4 datasets, although NLDF, C2SNet, and PRM use extra training data. Our method still outperforms them. We conduct 2 operating studies. First, with the contribution of different losses are evaluated. The result shows that each of the proposed losses is useful. Second, the co-sense map are also useful for this task. Show more examples of our approach. The first one is airplane. The second one is bird. They are good. And the third one is cow. In this work, we present a new test called instant co-segmentation and deliver a simple solution. Our method is simple. It does not any change stage or annotations. 4 datasets are collected for evaluation. Our method achieves the state-of-the-art performance. Thank you for your attention. The code and dataset are available. If you have any question, please come to my post with ID 58. Okay.
Good. Hello, everyone. So this is Yizhu from University of California, Merced. So in this talk, I'm going to present our work on semantic segmentation in driving scenes. This is a joint work with my colleague Karan, Pham, Kevin, Andrew, and Brian at Media Research, and my advisor Xiong. In standard semantic segmentation pipelines, we use manual annotated image label pairs as input and train a deep neural network to learn the mapping between them. However, it is very expensive to collect a large-scale dataset due to the per-pixel annotation process. For example, annotating a 1K by 2K image in Cityscape dataset takes about 90 minutes. But we noticed that for autonomous driving, we usually have access to unlimited video recordings as the car drives around. We just don't have enough ground truth. The data is labeled only sparsely. So we wonder, can we use adjacent unlabeled video frames to help improve the performance of semantic segmentation? There is a previous approach to do this called label propagation. The idea is to first learn a transformation function given video frames and such as OptiFlow, and then use a function to propagate semantic labels to adjacent frames. This method has several limitations, like problems resulting from occlusion and misalignment. In this work, we propose a data synthesis method based on video prediction to create more training samples. We exploit the prediction model's ability to predict the future frames in order to also predict the future labels. The video prediction network can be trained in a self-supervised way to learn how objects move between frames. This can effectively handle the occlusion problem. In addition, we observe that for traditional label propagation, there is often a misalignment between the ground truth video frames and propagate labels due to inaccurate motion estimation. We show two examples here, the distorted street pose and distorted human legs in the propagated labels. In order to obtain more accurately aligned image label pairs, we propose joint propagation. Instead of using ground truth video frames, we use propagated frames. Although the propagated frames might not look as realistic as the ground truth frames, they match perfectly with the propagated labels. This simple strategy is crucial to learn an accurate model since semantic segmentation is a dense per pixel estimation problem. Using our approach, we can scale up the training set in an autoregressive manner by propagating over more and more time steps. Here, we show some propagated training samples. We predict from 5 past frames to 5 future frames. Only the middle one has ground truth, while the others are all predicted. If you look at the rightmost column, we can see how the method can generate useful data for us. However, synthesis of data often has artifacts. We observe that for a model has high uncertainty around class boundaries. We therefore propose a modification to the class label space that allows us to predict multiple classes at boundary pixels. Simply speaking, we de-emphasize learning of border pixels from the augmented data. This technique helps our training process be robust to label noise. For results, first, we compare our video prediction model to optical flow. Visually, we can see that a video prediction network can handle occlusion much better than FlowNet 2. And quantitatively, the video prediction network also performs FlowNet 2 at all propagation lengths. Next, we show the effectiveness of label relaxation. With label relaxation performs much better than without it at all propagation lengths. We can now benefit from longer range training data propagation. We also show some favorite examples to demonstrate the advantage of our proposed method. We can see that the bicycle is segmented from the pedestrians correctly. The signs are segmented as a whole. And the fences can be distinguished from walls. Quantitatively, we achieve state-of-the-art results on 3 benchmark datasets, Cityscape, ChemVid, and Kitty. To conclude, we propose a semi-supervised learning pipeline to utilize unlabeled video frames to improve semantic segmentation performance. I want to point out that our techniques are general. You can use pre-trained video prediction model to augment your dataset regardless of whether you have video data or not. You can also use image label propagation to handle misalignment in other vision tasks. You can also use boundary label relaxation for any dense per pixel estimation problem to address label noise. For more information, please check the QR code and come to our poster at 59. And our code is just released on immediate semantic segmentation. Thank you.
Hey everyone, my name is Samvit, and I'm from the RISE lab at UC Berkeley. Today I'm going to talk about our paper, Excel, a corrective fusion network for efficient semantic segmentation on video. First, a brief recap. Semantic segmentation is a task of mapping every pixel in an image to an object class. Unlike other related tasks, semantic segmentation entails classifying every part of the image, not just objects of interest. Over the last decade, we've seen substantial evolution in architectures for semantic segmentation. Fully convolutional networks have become the de facto standard, and researchers have proposed various network augmentations in the pursuit of higher accuracy on more challenging data sets. As a case study, we can consider 2 points in this evolution, the original FCN network from 2014 and DeepLab v3 from 2017. Within this time span, accuracy has improved by nearly 25 percentage points on the Pascal VOC dataset, but the hidden cost of this gain has been an almost 5x increase in inference time to about 750 milliseconds per frame. These inference times become particularly problematic when we move to video. Modern video introduces 3 axes of complication not present in simple images. Modern video is shot at high frame rates, at high frame resolution, and is often captured by a moving observer in a complex environment. This makes frame-by-frame evaluation of heavyweight image models like DeepLab cost prohibitive. In 2017, a team from MSR Asia proposed a new approach to video semantic segmentation. Their system, called Deep Feature Flow, builds on the insight that nearby video frames tend to be very similar, allowing representations to be cached and reused across frames with minimal modification. Specifically, they proposed that features be extracted on designated keyframes, say every 5 frames, and warped to intermediate frames using optical flow. Since warping with optical flow is much cheaper than recomputing features, this saves substantial computation. Deep Feature Flow, however, faces a fundamental challenge: accuracy degradation, introduced by repeated warping. There are 2 reasons for this. First, warping with a flow field is a coarse operation in and of itself. And second, spatial warping ignores certain kinds of temporal change. In particular, it ignores any kind of scene evolution that is not in motion, such as the appearance of new objects, occlusions, and lighting changes. Our solution to these problems is a new network architecture for video semantic segmentation that we call Excel. Excel is a 2-stream fusion network that combines 2 network branches. The first branch, called the reference branch, shown in blue, incrementally warps features from the last keyframe using optical flow, just as in Deep Feature Flow. The second branch, called the update branch, is a lightweight single-frame segmentation network repurposed to perform per-frame temporal correction via joint end-to-end training. This branch, shown in green, serves as a residual pathway that introduces signal from the current frame and corrects warping-related error. Finally, Excel fuses the 2 branches just before the softmax layer in a convolutional score fusion step. Excel is modular. While the reference branch always uses ResNet 101 as its base architecture, the update branch in the second column is configurable. In particular, using ResNet 18 in the update branch enables a competitive high-speed version of Excel called Excel 18. At the higher accuracy end, using ResNet 101 in the update branch enables an extremely high accuracy version of Excel called Excel 101. As these plots indicate, the Excel models, shown in red, form a family of networks that outperform their competition, including both the single-frame deep lab models, on which they're based, shown in blue, and various related work, including Deep Feature Flow. In particular, Excel 18 is both more accurate and faster than Deep Lab 50, and Excel 101 exceeds state-of-the-art accuracy on both Cityscapes and Camvid. At its core, Excel addresses the warping-related accuracy degradation problem of its predecessor, Deep Feature Flow. Even at the very sparse keyframe interval of 10, Excel models maintain between 70 and 75% MIOU on Cityscapes, while Deep Feature Flow accuracy falls to 60 MIOU. Here are some example segmentation outputs at keyframe interval 10. On the top left, we have Deep Feature Flow, which also serves as Excel's reference branch. Note the substantial warping-related artifacts behind the truck. On the top right, we have Deep Lab 18, which is the architecture for Excel's update branch. Note the misclassifications on the truck, which result from low feature resolution. Finally, on the bottom, we have Excel 18. Note the consistent accuracy across the sequence and the clear visibility of the pedestrians in the background. Finally, please make sure to stop by our poster today, poster number 60. Thank you very much for listening.
Questions? Could you come to the
I have.
mic?
So the label relaxation parameter, is that a hyperparameter, or how do you get that?
I'm sorry, can you repeat the question?
For label relaxation,
Yeah,
how do you do that? Like, do you learn?
Label relaxation, we did it on the data set. So originally, it's one hot encoding, right? So for 19 class, you only have one class. But then we changed the data, so it's like we can do multi-class prediction. So like maybe car, bicycle, so they can be the single class. So there were multiple ones, so it's multi-hot encoding. Yeah.
I have a question for the Excel paper. Here? Yep.
Excel. Okay.
Over here. You're on the side?
Okay.
Thank you. Very interesting approach. At what resolution do you process the update branch, the Excel branch?
That's a good question. So we process it at the original resolution.
So how do you get acceleration if you still need to process every frame at its original resolution?
So that's where the varying feature subnetwork comes in. So when we process it with ResNet 18, the final feature output of that is lower resolution than when we use ResNet 101. So if that's what you were getting at, yes, we do process. We look at lower resolution features in the update branch for the acceleration result. But we look at the original image at its original resolution.
Can you consider processing only part of the frame? Can you predict what regions of the next frame you need to focus on?
Sorry, could you say that again?
Instead of processing the entire next frame for the update, can you do something more clever than predicting where you need to focus on the next frame and process only parts of the next frame, not only in lower resolution, but even ignoring parts?
Right, that's an interesting idea. Actually, we started with that idea and considered maybe just resegmenting portions of the image that demonstrate like substantial motion or substantial change that's not captured in the optical flow field, and kind of actually evolved to this approach. But yeah, that's a potential also promising direction.
Thank you very much.
Thank you.
Good morning. My name is Yahao Shi from Beihang University. I'm very glad to give my presentation about this paper named Shape to Motion, joint analysis of motion path and attributes from 3D shapes. Given a 3D shape as a static observation, then to segment motion path and estimate its motion attributes, then we can make the segments move. In most existing approaches, mobility analysis is conducted on pre-segmented parts of a 3D model. However, not all semantic segments imply a mobility. Another type of method extracts mobility through comparing multiple different motion, but not all mobility can be supported by motion state comparison, such as a rotating sphere. There are 3 contributions of this paper. First, we propose the problem of joint analysis for motion path segmentation and motion attribute prediction from a single 3D shape. Second, we designed the first deep learning network to approach the above problem. Third, we contribute the first benchmark of 3D shape mobility analysis. Next, I will show you the complete framework in this paper. We use single 3D point cloud as input. We use mobility proposal network to propose motion path segmentation and the corresponding motion attribute. Besides, it can select good quality mobility proposal with access. We use mobility optimization network to refine the predict segments and its access. By using post-processing method, we can merge the segments into a whole output. The network details are as follows. MPN is composed of 3 modules. Motion path proposal module predicts similar matrix and the consistency map. Each row of the similar matrix is the 1-0 mask represents a segment. Motion attribute proposal module predicts the axis. Each axis is represented by start point, direction, and motion type. We predict anchor point and regress displace between anchor point with axis to get start point. We discretize the space of a rotation into 14 candidates. For each axis, we choose one rotation and regress the residual vector. Last, we classify the mobility into 3 motion types: translation, rotation, and spiral. Proposal matching module is designed to regress the matching score, which we can choose a better axis for each segment. MON is used to refine the predict proposal and its axis. This network has 2 branches. The static branch inputs an original point cloud, and the dynamic branch inputs a bunch of move point clouds corresponding to the mobility being refined. After processing method, we get final result. Next, I will show you our benchmark dataset. Our dataset consists of 2,519 3D models covering 45 categories. Obviously, mobility annotation is tedious. To ease the process, we developed an annotation tool. Our annotation tool consists of two parts, motion part annotation and motion attribute annotation. A notable feature of our tool is it allows the user to visually verify the correctness of an annotated mobility. To compare with the state of the method, we use LU to measure the segmentation and EPE to evaluate the 3D motion flow. Minimum distance and orientation error measure the start point and the direction. TA is the accuracy of the motion type prediction. We get high performance thanks to the motion-driven strategy. We also get high performance than Hoot's method using Hoot's dataset. Besides, we have an analysis of parameters and networks. You can refer to the paper for more details. If you have any questions, please contact this email, and you can visit this link to get code and dataset. That's my presentation. Thanks for attention.
Hello, everyone. Welcome to our work, Semantic Correlation Promoted Shape Variant Contest for Segmentation. I'm Heng Hui from Nanyang Technological University, Singapore. Contest is essential for semantic segmentation. However, most existing methods are spatial dependent contests with a predefined fixed window as a rectangle region for the pixel A in the image. However, this kind of contest weakens the semantic shape layout and might bring unnecessary and irrelevant information. So in this work, we propose to aggregate context from the semantic dependent region to aggregate more desired surrounding information, as shown in the lower right image. And this kind of contest is more close to the ground truth. To this end, we propose a shape variant contest to enhance the semantic correlated features, but suppress the unrelated features. In such a way, every pixel has desired context region that supports its character prediction. In order to get the correlated region, or the semantic correlation, we first propose a paired convolution to learn the shape mask that represent the semantic correlation. As shown in this figure, each feature in the paired convolution generates a correlation value between the tagged pixel and other pixels, and save it to the position with the same color in the shape mask, as shown in the 4 different colors in this figure. Here is the architecture of the proposed shape variant contest. We use 2 branches. The upper branch is to generate a shape mask for every pixel. In the upper branch, we use a paired convolution to calculate the correlation values and save them to the channels for each position. Then those correlation values are reshaped to generate shape masks. And those masks are used to get the convolution process to aggregate shape variant contest for different positions. And in such a way, with the shape variant contest, we can help to control the information flow within the network by deciding what information to be parsed or suppressed. We visualize some shape masks here. As shown in the figure, the shape mask varies with the image and the pixel. Different pixels have different shape masks. Thus, they can aggregate surrounding information from the semantic correlated regions instead of the predefined fixed region. And we also analyzed two most common labeling errors in the segmentation. The first one is the in-context error, as shown in the first row in the image. This kind of in-context error is mainly caused by the inaccurate positioning and the influence of inter-context within these images. And the second error is the out-context, as shown in the second row. This one is mainly caused by the inaccurate classification. And in this work, to mitigate the out-context error, we propose a labeling denoising model to remove the noisy information from the low-level features in the process of decode to remove the noise information. And we tested the proposed network on 6 different segmentation datasets, such as parser context, CocoStar, and cityscapes. We achieved very good performance on all of those datasets. And thank you. Welcome to our poster for any questions.
Good morning, everyone. I'm Binh-Son from Chinese Academy of Sciences. I'm glad to share our work, Relationship CNN for Point Cloud Analysis. The project page can be found through this link, where you can get the source code. Firstly, I want to clarify our motivation. As we all know that the 2D image is made up of RGB values. If we remove these values, the cat hair is disappeared and we can see nothing. However, it seems different for 3D point cloud. If we remove the attributes of this colorful rabbit, it is still here. So here we think the key information is the spatial layout of these points. Therefore, we only need to find a way to calculate the spatial layout of these points. Under this motivation, we think the relation among points could be an explicit expression about the spatial layout, since the points are in general not isolated. So, in order to capture the underlying 3D shape, we can apply CNN to learn from the relation between a point and the others. To achieve the relation learning, we propose a relationship convolution. To be specific, we first sample several local point subsets as the spherical neighborhood. Then we formulate a general convolution on points analog to the classical 2D convolution. That is, the convolution result is obtained by first transforming the features of each point with a function t, and then aggregates all the transformed features with a function a. For this formulation, the permutation invariance requires the function a to be a symmetric one, and t is shared. However, in the classical CNN, t is not shared, and the gradient in backpropagation is only relevant to a single point. No relation between points is captured. To address these issues, we convert Wj into Wij, letting Wij learn a mapping from Hij, the predefined geometric priors. Here, M is implemented by a shared MLP, whose function is to map the low-level relation Hij into a high-level relation encoding. Finally, with a symmetric function A, we can get a result that not only holds permutation invariance, but also aggregates all the relations between a point and its labels. The proposed relationship convolution is composed of two parts: the high-level relation encoding and the channel relation mapping. Here, the low-level relation Hij can be defined flexibly. In paper, we use a 10-dimensional vector. Using this relationship convolution as a basic operator, we can easily build a hierarchy like classical CNN, which we call relationship CNN. The proposed relationship CNN has been evaluated on 3 different tasks for point cloud analysis, and it gets very good results on all these tasks. We also visualize the feature response learned by the network. As can be seen here, the early features mostly respond to the corners and edges, while deep features capture more symmetrical shape parts, like the aircraft wings and human hands. This is similar to the classical CNN on images. Finally, we explored some intuitively predefined relations. We can see that even using a single Euclidean distance, our method still gets very good results. In addition, we think the relation among points on a 2D view can also reflect the underlying 3D shape. So we project the 3D point onto a 2D plane and still get very good results. This is interesting, showing the ability of our method to capture the underlying 3D shape from the 2D views. Okay, that's all. Thank you and welcome to our poster.
Any questions?
I have a question for the semantic correlation work. How does your work relate to non-local network?
Pardon?
Non-local
non-local, you mean?
Non-local layer in nets that does spatial attention. It's also common in video.
You mean the non-local attention work?
Yes.
Yes, our work shares some similarity with the non-local, and maybe we have difference with how to calculate the semantic correlation, because we observe that the features of the with the contextual information they are frequently coexistent in the data sites, so they share some similarity. And thus, we calculated the difference, the distance between those features, and then map the difference to the semantic correlation. And actually, we are a kind of shape position variant convolution process. And okay.
And basically, you assume independence of the class label given its surrounding. So you basically condition the class label on the actual segment that you roughly compute by the correlation.
Yeah. So your question is, what's your question?
So basically, for each pixel, you look at the correlation and you compute a mask that quite align with the actual segment.
Yes.
And then you disregard all the surroundings. So it seems like you condition on the segment and you are making yourself independent of the surrounding, of the context.
Yeah, we calculate the shape mask for every pixel, and we use this shape mask to mask the convolution. And another difference between our non-local is only attention method, but our method is combined with the convolution. We also want to calculate some spatial dependent, so we also use the convolution. So we calculate the...
I'll have to interrupt you because we have to enter the next session.
Thank you.
Okay, so take it offline on the poster, thanks. Thank you.
Good morning, everyone. My name is Zhao. In the following talk, I would like to share our recent research on enhancing diversity of defocus blur detectors, where cross-ensemble network. Defocus blur detection is a fundamental topic in computer vision. The goal is to highlight the defocus blur region in an image. DBD is of broad interest for potential applications. For example, deblurring for restoring partial blurred images, image matting for extracting foreground objects, blur magnification for highlighting salient objects. Recent works have resulted to the CNN, which have set new state of the art on DBD. For instance, a successful deep and wide CNN for DBD is MSBTBNet. However, the CNN-based DBD method have two aspects of limitations. One detector lacks diversity. Two, deeper and wider network results in loss of parameters. In this work, we contribute from the view of adopting the division of labor method by breaking it into multiple smaller defocus blur detectors. Thus, these estimate errors may cancel out each other, hopefully reducing the final DBD error. Here, we focus on two concerns. One, how to enhance diversity of these detectors. Two, how to implement network with less parameters. To enhance ensemble diversity, we propose a CE-net, which is constructed with two groups of detectors. Each detector is not only negatively correlated with the other detectors of the current group, but also with the ones of the other group. For the loss of each detector, the first item is to assure accuracy. The second item aims to enhance diversity of the current group, and the third item focuses on improving diversity with the other group. CE-net includes two subnetworks, FE-net and DBE CE-net. FE-net is constructed to extract low-level features. Then the features are fed into DBE CE-net, which contains two parallel branches for learning two groups of detectors. Finally, the multiple detectors are combined with a uniformly weighted average to obtain the final DBD map. We adopt an iterative training strategy to train CE-net. We first train FE-net and one branch of DBE CE-net. Then we fix FE-net and initialize the other branch with trained parameters of the first branch. Finally, we fine-tune the two branches of DBE CE-net in an iterative way with every epoch. Here, we show some examples to compare the visual and quantitative results by ours and others. As can be seen, our method outperforms the state of the art in terms of accuracy and speed. Thank you.
Hello, everyone. Thank you for being here today. My name is Brent Griffin. This work is done in collaboration with Jason Corso. And today I'm going to be talking about our work on bubble nets. With the introduction of high-quality data sets like Davis, we've seen many new video object segmentation methods being developed. Among these, this work focuses on improving the performance of semi-supervised algorithms with no changes to the underlying method of segmentation. The current paradigm for semi-supervised video object segmentation is for a user to annotate an object in the first frame, and then let the algorithm segment this object in the rest of the video. However, we found that if this annotation is provided in a different frame, the segmentation performance can change dramatically. And this can be for better or worse, depending on which frame is selected. These changes occur due to changes in temporal proximity and similarity to other frames, as well as view and pose of the annotated object. To make the best use of an annotator's time, we should use the best frame possible. The goal of BubbleNets is to learn to automatically make this selection in an untouched video. BubbleNets makes relative predictions between frames to iteratively compare and sort frames adjacent in the video. And after this sort, the frame with the best predicted performance is then selected for user annotation, which we show in our paper to result in better segmentation performance. Let's talk about how we build the labels that we use to train BubbleNets. Using the Davis 2017 training set, we have 60 videos with dense ground truth annotations for various objects. Using the OSFOS segmentation algorithm, we first train OSFOS using first frame annotation, and then evaluate OSFOS's performance over the remaining frames of video using the Jacquard measure and contour accuracy. Similarly, we can use the second frame annotation instead, and then reevaluate the performance of OSFOS over the video. And when we replicate this process across the video, we produce a training label Y for each frame, representing the segmentation performance associated with selecting that frame for annotation. Let's talk about how we use these frames to train BubbleNets. While it would be straightforward to just use the entire video as input and train BubbleNets to predict the frame with the best performance, this only gives us 60 training examples, or one training example per video. Alternatively, if we independently evaluate each frame and predict its individual performance, we can use a loss that gives us n training examples per n frame video. Better still, in this work we use what we call relative frame performance. In this way, we use two input frames and predict the relative difference in performance associated with using either frame for annotation, and we're able to develop n squared training examples per video, or 750,000 training examples from the initial 60 videos. The BubbleNets architecture follows this relative frame performance formulation, and we have two input frames I and J that are pre-processed through ResNet 50. To provide some context for the rest of the video, we select 3 frames at random, and we also provide these as input. And the last input into our network is the frame index of each frame. These are provided to each one of the performance prediction layers, and the final output of the network is the predicted relative performance of the 2 frames being compared. We trained this network using the relative performance loss from the previous section. And once BubbleNets is trained, we can now select that annotation frame in an untouched video. We do this using BubbleNets in our deep bubble sorting framework. And this starts by comparing the first 2 frames. If the first frame is predicted to have better performance than the second frame, its position within the swap is switched with the second frame. After this potential swap, we move on to the next adjacent pair and start a new comparison. And in this way, we can iterate in a bubble sorting manner through the entire video. And after the sort is complete, BubbleNets has selected the frame that it predicts has the best performance. And this is then determined to be the one that the user should annotate. And we show in our paper that this improves the performance of segmentation. You can see this on the bubble sort results on the right. And you can also see this when we look at the output segmentation associated with BubbleNet selected annotation frames versus first frame annotation. And we provide quantitative results on the Davis 2017 validation set and other data sets in the paper. And the first thing that we note is that first frame annotation, which is the current standard in benchmark data sets, only outperforms selecting the last frame. Even randomly selecting frames is a better strategy. Middle frame selection is the best of the naive frame selection strategies and is easy to implement. But BubbleNet selected frames result in the best segmentation performance, with an 11% improvement over first frame annotation. We also want to emphasize that even though BubbleNets is trained exclusively on OSFOS-generated training labels, it selects annotation frames that also improve the performance of other segmentation methods. But if you had another segmentation method you really cared about, the label generating formulation is general, and you could generate more labels for that method. Thank you for coming to this talk today. If you'd like to use BubbleNets in your own video processing applications, please visit our GitHub page at the address shown here. And if you'd like to learn more, please come talk to me during the poster session or check out our paper. Thank you.
Hi, everyone. My name is Yeung. Our work is collaborative global local networks for memory-efficient segmentation of ultra-high resolution images. We are from the CS and the ECE department at Texas A&M University. The goal of semantic segmentation is to assign each pixel a class label. Recent models work on full resolution images, which requires more GPU memories than classification and detection. Popular datasets like Cityscapes, COCO, and VOC contains middle to small images, which makes the cost of GPU memory hidden and negligible. However, this problem becomes significant when the image resolution grows to be ultra-high, which are rarely studied in segmentation. Datasets like Deep Globe, iSeq, and In-Real Area contains ultra-high resolution images up to 30 million pixels, leading to a dilemma between segmentation quality and memory efficiency, or even feasibility, during both training and inference. With limited GPU memory, two ad hoc ideas are downsampling the global image or cropping it into patches. However, we can observe that model trained with global images suffers from jiggling artifacts due to the missing details. And in comparison, model trained with local patches lacks neighborhood dependency, making it difficult to distinguish visually similar regions. We propose our collaborative global local networks. Our GLNet is composed of a global and a local branch, taking both the downsampled global images and cropped patches. It deeply fuses feature maps from two branches, preserving both the global and the local context in a highly memory efficient manner. We also add the branch aggregation module and the regularization module to make the final dense prediction from the two branches. We enable our deep feature map sharing in each layer. The global feature maps are first cropped and downsampled and upsampled to match the size of the feature map, local feature maps, and are concatenated as channels onto the local branch. Symmetrically, the local feature maps are also downsampled and reassembled at the same order in which the local patches are cropped, and are also concatenated as channels onto the global branch. We also add a weekly collaborated regularization module to avoid the local branch from learning too much faster than the global branch. And we also use two auxiliary losses to make the training stable. Our GLNet achieves the best trade-off between accuracy and the memory usage, which locates in the top left of the plot. Other state-of-the-art models achieves high MRU, however, they consume much higher memory usage. We also select the FCN and ICNet for in-depth comparison. Results show that they achieve poor trade-off between memory usage and accuracy with either global images or local patches. In ultra-high resolution, the foreground region usually is far less than the background, which may seriously damage the segmentation performance. To resolve this class imbalance problem, we propose a coarse-to-fine two-stage segmentation approach. It first applies the global branch as the coarse segmentation on the downsampled global images, and the bounding box is created on the foreground, and only the bounded foreground region is fed into the local branch for the fine segmentation. And the histogram shows that the imbalanced foreground-background ratio by the red bars is successfully shifted to the balanced blue bars. And ablation on the iSeq dataset shows that our GLNet achieves the best result, and with the bounding box aided two-stage segmentation, and still maintains the best trade-off between memory usage and accuracy. For conclusion, we argue that pursuing an optimal balance between memory usage and accuracy is essential for studying the ultra-high resolution images. And our proposed GLNet can leverage both the global and the local context effectively to enhance the segmentation for ultra-high resolution images without sacrificing the GPU memory usage. And finally, the class imbalance problem can be further solved by our coarse-to-fine segmentation approach. Thank you very much.
Please go up. Questions?
Yeah, I have a question for the BubbleNet paper. How would the recommended frame maybe change if the class were different for the object that you're labeling, or if you decided to label a different object than the one that was maybe intended in that video snippet?
So when BubbleNets is deciding which frame it's going to select for user annotation, it has no idea what the user intends on annotating. So it's a very challenging problem, but that's why we're saying selecting that frame in an untouched video. But nonetheless, we're able to show that even though you don't know the object in advance, we can still use information in the raw video to determine a frame that's going to be more beneficial than the first frame.
Okay, so maybe it's kind of making a guess at which object you might be.
Yeah, it has to make a guess. And I think like a future extension of this work would certainly be if you had some more information, that could certainly be leveraged to make the decision. But we're operating under the assumption that the user's provided no clues at this point. So it's like a pre-processing for selecting the annotation frame.
Okay, thanks.
I have a question for paper number 3. How do you, I assume the downsample version and the patches are the same size.
Yeah.
So how do you, have you studied how the effect of varying sizes?
Yeah, exactly. So if you have time to take our the supplementary, we have the in-depth comparison with different global image size, downsample global image size, or the cropped patches. And we can observe that with different sizes, our network can still maintain the low memory usage, even with much larger image or patch sizes, and still maintains the high accuracy.
But the issue is a little bit more complicated. It depends on what the scale of an object you want to segment. For example, if it's overhead images, you have roads, which are thin structure. If you downsample, your local patches preserve the details, but if the global image is too large and your feature extracted from the smaller global image is going to dominate, the feature represented could dominate the local patch feature extraction. So you won't be able to get, the performance on those thin structure will be much worse.
Yeah, thank you very much. I think this is a good question because our Appalachian study really provides the flexibility to choose the different sizes of both the global image and the local patches.
Okay, thank you.
Thank you.
Yeah, thank you, sir.
Hi, my name is Sai-Kit, and I'll be presenting our recent work on a new clustering algorithm we term as Finch. Automatically discovering groupings in the data is needed in all areas of sciences. The current limitations of the clustering algorithms includes their over-reliance on hyperparameters, their ability to generalize across different data scales, and the scale to large data. We address some of these limitations and present an efficient and fully parameter-free clustering algorithm. It, for example, can cluster 8 million samples in 18 minutes versus k-means that take 56 minutes on a single machine. Our proposal is based on an important observation that the very first neighbor of each sample can form large linking chains in the data. Since only the first neighbor is required, which we can get from approximate nearest neighbor methods, we do not need to keep all pairwise distance of the sample in the memory. We show that with only the integer list of these neighbors, we can produce natural groupings in the data, and thus no threshold or hyperparameters have to be set. We capture this observation in our proposed single clustering equation, which specifies 3 conditions to form the Jensi link matrix. The symbol K1I represent first neighbor of point I or j, which are linked together when either of these conditions are met. Intuitively speaking, these conditions are combining the first neighbor and shared neighbor graphs. The clustering equation directly specifies that Jensi link matrix whose connected components are the cluster, so no further analysis such as solving the graph segmentation problem is needed. To understand the conditions better and how they form large clusters, let's look at a small tractable example of clustering the planets in our solar system. We can cluster the planets in their known measurement space, such as diameter, orbital period, taken from NASA fact sheet. In this space, the first neighbor of each planet, according to Euclidean distance, depicted on the table on the right. With this information, we can form a 9 by 9 Jensi link matrix. The first condition simply connects all points to their first neighbor. An important observation is that not all samples are symmetric. For example, Earth is the first neighbor of Venus, but Venus is not the first neighbor of Earth. Such samples are also the reason for inducing large linking chains in the data. A second condition simply enforces symmetry and links such samples together, while the third condition links points together who share the same neighbors. For example, Earth and Moon are linked together because they have the same neighbor, Mars. As shown on the directed graph of the adjacency link matrix, the clustering equation has discovered 3 clusters. Note how 5 out of 9 samples are merged into one cluster, while the 2 symmetric pairs form 2 separate clusters. Interestingly, astronomers also use the same groupings of this data. Clustering equation delivers a flat partition with some predetermined clusters. Applying it recursively produces further successive partitions of this. Doing this is useful as it enables us to have hierarchy of clusters. Since the clustering equation makes large merges, applying it recursively converges in only few steps, providing a small set of hierarchical partitions. Applying recursively means that at each step we need to merge clusters, finding first neighbor of each cluster. This is based on the cluster means. We tested Finch on data of different sizes and dimensions, from 1,077 to 8 million, represented in 77 to 4,096 dimensions. And we compared with a lot of existing clustering baseline, including both classic and state-of-the-art clustering methods. The results are pretty good. You can come see them later on our poster. Here we show how the algorithm converges while producing meaningful merges. The left plot shows the convergence. At each step run, Finch produces a partition of the data. We plot the number of steps run for the algorithm in several data. This can be seen in only few steps we produce a hierarchy of partitions. For example, the smallest 1,000 sample mice protein data Finch delivers a total of 6 partition, coming down from 1,000 to 351 in the first, to ground truth 8 cluster in step 4. While on the right plot, the cluster produced at each step maintains a high accuracy, indicating that the clustering equation delivers quite meaningful merges. Since Finch operates on integer list of first neighbor indices, therefore the scheme is extremely fast and very memory efficient. As seen, the complete computation timing of Finch, including everything, is pretty nice. We can cluster more than 8 million samples in 18 minutes on a single CPU machine. So to sum up, we propose a single clustering equation that captures groupings in the data. Our algorithm is quite efficient and does not require any user-defined hyperparameters or other a priori knowledge. This may have potential to discover natural groupings in the data. The computational complexity of Finch is of n log n, and the memory efficiency is of n. Discovering groupings in this way is very useful in practical applications. For discussions and more insights on the detailed results and comparisons, please come to our poster number 67. Thank you very much.
Hello everyone, I'm Liao from San University. Today I will present our work learning personalized modular network guided by structured knowledge. The dominant deep learning approaches uses a one-size-fits-all paradigms with the hope that the underlying characteristic of diverse input can be captured via a fixed structure, regardless whether the inputs are too easy or difficult for network capacity. However, different examples actually need specialized network structures or feature propagation routines with respect to their different complexities and specific targets. For example, 3 different cat images. The motivation of our PMN is to mimic this dynamic reasoning system of human perception to adaptively allocate time and inspection for visual recognition and to learn dynamic module configurations to infer personalized reasoning paths, and to bridge visual feature hierarchy with common sense human knowledge. Our PMN aims to learn different module computations for each input, and each module is to recognize concepts of distinct knowledge levels given a basic network structure and their prior structural knowledge. So learning to sequentially select modules for addressing particular levels of knowledge can be formulated as a sequential decision-making procedure. We propose a new graph-based reinforced learning algorithm, which specifies the varied knowledge level set at a particular action set for each network module, driven by a graph search function. Particularly, the action space of each network module enforces early modules characterize easy knowledge, while the later modules are responsible for more fine-grained knowledge. A recurrent policy network is learned to reason over the involved action space. And the reward function encourages both early stopping your network propagation and better balance over efficiency and accuracy. Given an action history of previous modules and their whole knowledge graph, the graph searching function finds an involved action space along with their graph structures. For example, the action space for first-level modules includes an entity, object, and produce. And the policy network selects the best action, such as object. And the action space of the next level modules will become the two-hop children nodes or activated graph nodes. And the inclusion of two-hop children nodes will allow skipping over some useless intermediate nodes in a deeper graph rather than strictly only activity their immediate children. In this way, our network can dynamically configure shallow networks for easy images and configure a deeper network for difficult images. Our proposed PMN is generally applicable to various tasks. Here we choose the image recognition as the running examples. Experiments are conducted on both Semantic-Instance on CocoStar, Pascal contest, ETH and image level classification. For example, CIFAR 10 and CIFAR 100. Our PFN can achieve better performance with less module uses on our dataset, which demonstrates the effectiveness of infer meaningful and individualized module configuration for each image. By comparing our graph searching policy with other policy strategies, such as fixed random and evenly distribution, our instance-specific and knowledge-aware policy learning can achieve the best result. So we also compare the different graph searching functions and demonstrate our model can achieve better results. And moreover, our PMN is able to provide a deeper understanding of feature representation learned in each module. It can be observed different modules are learned to recognize their specific knowledge levels and personalize the inference paths are activated for distinct inputs to activate final prediction. Thank you for listening. Please stop at our poster for more details.
Okay, my name is Joachim, and this work is done jointly with Martin, Emil, Fahad, and Michael. We investigate the problem of video object segmentation, where you're given a video with one or more targets marked in the first frame. The aim is to track and segment the targets throughout the video, and the targets are generic in the sense that you don't know anything about them beforehand. You only have this labeled first frame to go on. So most existing approaches are based on so-called online fine-tuning. And the idea there is to train a generic segmentation network offline, and then during inference, you fine-tune this network. Issue is that inference becomes very slow. Moreover, these approaches cannot be trained end-to-end because the offline training stage does not model the online fine-tuning. Therefore, some alternatives have been proposed, but they are based on very simple matching mechanisms that are not able to well discriminate the target from the background. There are also a couple approaches based on k-nearest neighbor matching, but KNN is not differentiable, so again, no end-to-end training. So what we propose in this work is to instead learn or model the appearance of the target and the background using a lightweight probabilistic model that you can easily formulate as a differentiable deep neural network module. And the approach obtains state-of-the-art results while being orders of magnitude faster than the online fine-tuning based approaches. So the first step in our approach is the appearance model learning. And I'll just wait a second. And first we extract the deep feature map from the reference frame. And this frame is labeled, so we know the class of each feature vector, whether it corresponds to background or to foreground. And we now want to probabilistically model the features conditioned on their class. And the key here is to select a probabilistic model that can be easily formulated as a differentiable neural network module. So in our work, we model the foreground features and the background features with one Gaussian each. And then the appearance model learning can be done using these two closed form expressions. So in subsequent frames, we want to apply this model. So we first extract a deep feature map, and we can then apply the model, the appearance model, together with base rule to, for each feature vector, calculate the probability that it belongs to the foreground and the probability that it belongs to the background, giving us a rough or tentative segmentation. And in practice, we calculate not the probabilities, we calculate the segmentation scores S, which are found using this differentiable expression. The scores are related to the probabilities via softmax. So the appearance model learning and appearance-based classifications are just two modules or layers within our full network. And the full network is coming in any second. Yeah, here. So in the first frame, we do the appearance model learning, and then we do the classification in subsequent frames and to gain these rough or tentative segmentations. And we then want to refine these. So we combine them with the deep feature map extracted in the test frame or in this frame and upsample that with the help of more shallow features, giving us a refined segmentation. To further improve this segmentation, we also fuse with the reference frame deep feature map, the reference frame label, and the prediction we made in the previous frame. We can also update the appearance model by treating the predictions we make as labels. And we train this entire network jointly on the video object segmentation task, or end-to-end on the video object segmentation task. So we try the approach on the YouTube Boss benchmark, and we first form a baseline by running without the appearance modeling, relying only on the other parts of the network, and we then obtain a score of 50. We then want to investigate the impact of end-to-end learning, so we add the appearance model, but we do not backpropagate gradients through the appearance model learning. And we then obtain a score of 58.8. If we remove this restriction, train everything end-to-end, propagating gradients through the appearance model learning, we obtain a final score of 66. So this demonstrates how crucial it is to be able to train your method end-to-end. Okay, let's see if my ending slide comes any second now. Yeah, so thanks for listening, and if you want to try or tinker with the approach, there is code and pre-trained weights available, and I look forward to meeting with our poster. Thanks.
Is there any questions? Okay, thank you all. Thanks, the speakers.